Hello and welcome to lecture 32. So this is the last lecture with new material that could potentially help you on the final. Okay, so let's jump into it. So claim 39. If x is a random variable from S to R and y is a random variable from S to R, where S is a sample space, then the expected value of x plus y is the same thing as the expected value of x plus the expected value of y. This is what's known as the linearity of expected value. And again, it's linear since this is kind of the definition that you use for linearity in pretty much all contexts. Okay, so for the proof, let's first note what these two terms here are. Well, the expected value of x, that's simply the sum of all s and s of x of s times the probability of s. Similarly, the expected value of y is simply this expression here. Thus, the expected value of x plus y, well, that, plugging it into the definition of the expected value, is simply the sum of x plus y, that as a function evaluated at s, plus the probability of s. Well, from here, how do I add functions together? Well, this expression here would simply be x of s plus y of s, all times the probability of s. So now these are all just real numbers, so I can distribute this out. So this is x of s times the probability of s plus y of s times the probability of s. So now I can split up these sums. I know this sum is over a finite domain or a countable domain, so I can freely do that. This sum will simply be this thing here plus this thing here. And now this is simply the definition of the expected value of x that I had up here, and this is simply the definition of the expected value of y. So from here, I get the result that I wanted. Okay, so one thing to note, this argument above can be adapted to work with finitely many random variables. So x1 plus x2 plus da-da-da up to xn, this process still works, or if you want to go another way, you could just simply use induction. Okay, so in some problems, I end up with something where I want to compute the expected value of the sum of lots of things. So in those cases, I can simply, instead of computing the expected value of the sum, I can compute the sum of the expected values. So that is a valuable property, sometimes for just saving some algebraic manipulations, and other times it can be crucial for a problem. So if there is a question like this on your final, it would just make it significantly easier, potentially, to compute an expected value. I'm not going to make it like a critical step for the final, since I'm, again, not testing you on this via homework before the final. Okay, one new thing we need to introduce, indicator random variables. An indicator random variable is a random variable that takes on one of two values, 0 or 1. So a classic example of indicator random variables is the result of a Bernoulli trial. This will always be an indicator random variable. You either pass or you don't. So these appear all over the place, and in some problems you can introduce an indicator random variable where you didn't initially start with one. For instance, in the next lecture when we talk about things, I will introduce indicator random variables there. Okay, so now let's look at claim 40. If x is an indicator random variable, then the expected value of x is simply the probability that x is equal to 1. So let's look at a proof for this. So for the proof, we know that the expected value of x is equal to this sum, right? So let's just expand this out. X takes on two values. It's either 0, in which case it's 0 times the probability that x is 0, plus, in the case where it's 1, 1 times the probability that x is 1. Well, this term here is always going to be 0, and 1 times anything is whatever the other term was. So this is the probability that x is equal to 1. So this might not look useful, but it is. In particular, it can be very useful when computing the expected values of Bernoulli type events. So if I did a Bernoulli experiment, say flipping a coin, hint at what is on the next slide, and I want to compute the expected value, then if I can simplify things out in the right way, I could use a combination of linearity and the fact that indicator random variables have this property to very dramatically simplify the problem. So let's do exactly this. Let's re-examine the problem of the unfair die from the last lecture. So recall the example of getting a fair coin flip out of a biased coin. Again, we can ask how many pairs of flips do we expect to need to do before we get a heads tails or a tails heads. So last time I had that really long drawn out way of evaluating this out. Now I can do this much quicker using the linearity of expected value and indicator random variables. So the first thing I need to do is build my indicator random variable. So we're going to define xi to be a indicator random variable that's 1 if the ith pair is ht or th, and 0 for any other value. So pretty clearly, this is a indicator random variable, right? It either takes on the values 1 or 0 with typo fixed. So now what I'm going to do is introduce a new variable. So I'm going to let r be equal to the sum from I is equal to 1 to n of this x sub I. So x sub I is a random variable, right? R is the sum of random variables. So the sum of functions is going to be a function. So R is itself a random variable. So what does R represent? Well, it follows that R is the number of pairs of tosses out of these n pairs of tosses where we can determine a fair flip. So in particular, if R is 2 and n is, say, 7, that means that 2 out of the 7 pairs were either heads tails or tails heads. So here's one of the main useful things of using pairs of flips instead of individuals. If I did individual flips, if I get a heads tails followed by a heads, then I have kind of 2 pairs. So that's just kind of a side note, but yeah. So now to solve this problem, I can rephrase it in terms of R. So explicitly, to solve this problem, we want to know on average what value of n do we need for e of r to equal 1. So here I say on average because there's randomness going on, but really I want to know what value of n gives me that e of r is equal to 1, or say maybe greater than or equal to 1. So why is this the case? Well, again, R tells me the total number of flips that were either heads, tails, or tails, heads. So if the expected value of R is equal to 1, then that means that the expected number of pairs of flips where I get a heads, tails versus or a tails, heads is equal to 1. So that tells me on average I have a flip that I can take to be my fair flip. Okay, so from here, I now want to compute this expected value of R. So let's go about doing this. So the expected value of R, well, by definition, R is this sum, right? So the expected value of R is the expected value of this sum. If I briefly tie this back into the previous question, this expected value of R was this expected value of F that I found before. So this was the expected number of pairs of flips that I need to get a heads, tails, or a tails H. So this expression here is the same thing, just written completely differently as this expression here, E of F, or this sum here. It's just written in a much more convenient form, since these x sub i's are now random variables that are doing all this heavy lifting of computing these various probabilities here. Okay, so now how could I possibly simplify this? Well, I have the expected value of a finite sum, right? And how can I maybe simplify this? Well, I know expected values are linear, right? So from here, I can take the sum and put it outside of the expected value operator. So this now goes from the expected value of this sum to this sum of these expected values. So now I kind of have a hint here, indicator variable. So these x sub i's are indicator variables, and previously I introduced a theorem of how I can compute the expected value of indicator variables rather quickly. In particular, the expected value of an indicator variable is the probability that the indicator variable is equal to 1. So from here, this finite sum simply simplifies to this expression. So now, do I know what this probability is? Well, yeah, I can compute it. So let's do that on the next slide. So the expected value of r is equal to this, and this x of I was the event that I either have a heads or a tails, or a tails or a heads. I computed that last lecture, or I could do it again real quick, but this is simply 2, so heads, tails versus tails, heads, times p, so the probability of heads, times 1 minus p, the probability of tails. So this is simply this sum here. So now you can note this thing does not depend on n, so this is just taking a number and adding it to itself n times. That's the definition of multiplication. So the expected value of r will simply be equal to this. So again, I want to know when the expected value of r is greater than or equal to 1, or in particular, ideally, I want it to be exactly equal to 1. So from here, I can just plug this in. So from there, this expression is the same thing as this expression, and now I can solve this for n. So n will need to be greater than or equal to this, and on average, n would need to be exactly equal to this expression. So do recall, this is the same result that I had from the last lecture, but I literally do this much algebra here plus this using a more sophisticated framework, as opposed to doing all of this stuff and dealing with this relatively nasty-ish sum in the middle. So yeah, same result from last lecture, but much less needed algebra. So when I say this can dramatically help simplify things on the final, this is what I'm meaning. If I give you a problem where I have Bernoulli trials or anything like that, this method will always be applicable, purely because Bernoulli trials are indicator random variables. And if I wanted like how many times you need to do it for this to be the case, this is the expression that you can compute. Okay, so this is the end of the testable material for this course. So if you really want to kind of skimp on trying to study that type thing, you can stop here. But I do recommend going through the rest of it. I think you'll find it more fun in nature. In particular, lecture 33 is all about real-world applications. So here we noticed that expected value was linear, right? The expected value of a sum is the sum of the expected values. A natural question we could ask is, does that work for products? The answer to that is sometimes. So in order to talk about the expected value of a product, I need to formally define it. So the expected value of a product or random variables x and y, given by this thing here, is simply this double sum over both x and y of x times y times the probability that x is equal to x and y is equal to y. So formally, this is really computing a probability of x and y here and multiplying it by this expression there. Okay, let's look at a couple of examples. So suppose we flip a fair coin twice. Let x be the random variable for the number of heads, and let y be the random variable for the number of tails. So a natural question I can ask is, does the expected value of x times y equal the expected value of x times the expected value of y? So here I can brute force my way through it. So for the solution, note that the sample space is simply this thing here, right? So from here, I can compute the expected value of x and the expected value of y straightforward. So the expected value of x will be the sum from x is equal to 0 to 2 of x times the probability that I have exactly x number of heads. So this would simply be this expression. So 0 times a fourth, that I have exactly 0 heads. 1 times a half, so that I have exactly 1 head, and 2 times a fourth, that I have exactly 2 heads. So if I compute this together, that simply gives me 1. So similarly, the expected value of y is the exact same expression where I just change x to y, and that's going to be this term here where I simply swap the order. So the number of ways that I can get, say, 2 tails would be this term here times a fourth, plus the number of ways that I can get 1 tail is this times 2 fourths, plus 0 times 1/4 for getting no tails, and again, that's simply 1. Okay, so on the other hand, x times y is a random variable for the product of the number of heads and tails. So there's a few ways that I can kind of think this through, but let's just kind of brute force it and then throw away the cases where things are trivial. So from here, thus, the expected value of x times y is this by definition, right? And now, what would this be as a sum? Well, it will simply be this term here, so let's see why. Okay, So if x is equal to 0, so if I have 0 heads, that tells me that I have exactly 2 tails, right? So when I pick a value for x, that forces a value for y in order to have a non-zero probability. So this double sum of going over all of the sums of x's and y's is not really a double sum. It's really a sum of the case where, say, x is equal to 0 and y is equal to 2. X is equal to 1 and y is equal to 1. And finally, x is equal to 2 and y is equal to 0. These are the only terms in this double sum that actually matter. Like the case where x is 0 and y is 0, that has a probability of 0 happening because that's an impossible event, right? So from here, I only need to compute the probabilities of these cases here. So for the first case, x is equal to 0, so I don't even need to compute this probability, I know it's 0. In the second case, x and y are both 1, so that's where I get the 1 times 1. And what's the probability of getting 1 heads and 1 tails? Well, of course that's a half, right? There's 2 options here that give me a heads and a tails, and there's 4 total options, so 1/2. And finally, in this last case, I have that y is 0, so this term is 0, so the whole thing is 0. So from here, the expected value of x times y is simply equal to 1/2. Well, I had the expected value of x and y were both equal to 1. 1 times 1 is 1. Does 1 equal 1/2? No. So in this case, this is not true, and the expected value of x times y is not equal to this. So one key element to notice in this problem, very clearly, x and y are not independent events. If I tell you what the value of x is, that guarantees the value for y. That's kind of violates the crucial basic idea of being independent. So if you wanted to formally prove that these events aren't independent, that would be a good thing to do. It's not too hard. You just plug it into one of those formulas for independence and see if it works, and you'll find out that it doesn't. Okay, so sometimes this isn't true. Is it true on other occasions? Well, I wouldn't be asking if it wasn't. So suppose we flip a fair coin and then roll a d6. Let x be the random variable for the number of heads, and y be the random variable for the results of the d3. Oops. Okay, anyways, so from here, does this equality hold? So one key thing to note before we even go into this, in this case, x and y are very clearly going to be independent events. They have absolutely nothing to do with each other. You can compute that analytically if you want good practice there. So let's look at the solution. So here I want to compute the expected value of x and the expected value of y. So for x, the expected value of this, well, that's simply this statement here. So 0 if I get 0 heads times a half plus 1 if I get 1 heads times a half, which is simply equal to a half. So that's pretty trivial. And for the coin, it's also trivial. It's simply 1/3 times this sum. So 1 plus 2 plus 3 is 6. If I divide that by 3, I get 2. So from here, if I compute the product of these expected values, I simply get 1. So now I need to do the hard work. I need to compute the expected value of the product of these random variables. Well, here, this would simply be the expected value of the product by this by definition. And here, very importantly, these events x and y are independent. Like flipping a coin and rolling a die are the classical examples of independent events. So they're definitely independent. So I can rewrite this probability of x and y as the probability of x times the probability of y. So I'm going to do that at the same time I simplify things out here. So this thing simplifies to here. Y. Let's break down each part. So x can vary between 0 and 1, right? It's either heads or I have no heads. So here the sum would be from 0 to 1. The sum for the second bit of the iterated sum, well, the results of a d3 could be 1, 2, or 3, so I want this sum. So then I want the product of x and y, as always. And here I'm doing two things at one time. I'm noting that the probability of a and b is simply equal to, well, x and y is simply equal to the probability of x times the probability of y. And just pretend I used curly brackets there. So the probability of getting heads, well, that's always going to be 0.5, right? Since it's a fair coin, whether x is 0 or 1, this probability doesn't change. It's always 0.5. Uniform distributions are nice. Next, the probability of y, well, whether y is 1, 2, or 3, since it's a fair die, I didn't say that, but I'm assuming it's a fair die, the probability is always going to be 1/3, so this is always going to be fixed. Okay, so now all the hard work's really done, and I can simplify this further. So here you can note for this outside sum, I'm summing from 0 to 1. In the case where it's 0, everything's 0, so I can just throw away the outside sum. Next, you can note that 0.5 times 1/3 is 1/6, and that's constant, so I can pull it outside of the sum. So this is 1/6 times the sum from I is equal to 1 to 3. Well, the sum from I is equal to 1 to 3 is just 6, so this is just 1. So 1 is equal to 1, so in this case, the expected value of the product is equal to the products of the expected value. It turns out that this is always the case. If I have independent events, I can always replace this here with the probability that x is equal to x times the probability that y is equal to y, and I can split up these sums to recover the sums that I would get here. So basically, if I wrote this out in terms of summation notation, I could rewrite this product in the form of this. So that sounds like it's a theorem. Let's name it as a theorem. Okay, so for random variables x and y, the expected value of x times y is equal to this product here, if and only if, drum roll, x and y are independent. Okay, so that's a useful little property, and this is actually more useful than you would think. In some sense, this property here is the basis for a significant portion of the field of statistics. So explicitly, every time you hear the standard deviation, it is actually related to this theorem and this quantity. Let's quantify that a little bit to be a little bit less hand-wavy. This quantity here, the difference between these, has a name. The covariance of x and y is denoted by COV often of x comma y is equal to this quantity here. So this is related to standard deviation, which is a term that hopefully you've heard before, but it's also related to another term. So have you ever heard of correlation? Well, likely, right? Lots of times people say things like correlation does not imply causation, things like this. Well, this quantity is not quite it, but the correlation is actually the covariance of, well, the correlation of x with y is actually the covariance of x with y divided by the square root of the covariance of x with itself and the covariance of y with itself. So here, if I just plug this into this formula, that's the expected value of x squared minus the expected value of x quantity squared. So in general, the lack of multiplicativity is a very important metric for statistics, and there's a significant amount of things you can do with correlation analysis and using correlation to try to prove, say, Granger causation. Yeah, this is a very, very deep topic. I just wanted to kind of dip our toes in a little bit by introducing this concept of the multiplicativity or lack thereof of the expected value. And one last thing, for those of you who are curious about how you actually compute the standard deviation, there's those handy formulas that are in some sense more useful for practice, but this standard deviation is actually the square root, well, here I need to put an x, but the square root of the expected value of x squared minus the expected value of x squared. So these terms here, if I expand out by definition, are equal to this, and that's exactly, well, the square root of this term here. So the square root of the covariance, that is actually, if you will, the standard deviation of the random variable x. So yeah, there's lots of deep connections here. This isn't a stats course, so we can't really get into the weeds, but I just wanted to show how important expected value is and how it ties into everything with stats, basically. Okay, so that is it for this lecture. We have a meme for you. Causation, correlation, civil war. So in general, causation and correlation aren't the same thing. In order to have causation, you need to have correlation, but having correlation in and of itself isn't sufficient to have causation. But sometimes you can have things that are correlated and you do have causation. That's a topic for much higher level courses on regression analysis, and in particular, time variant regression analysis. But yeah, so that's it for this lecture, and I will see you next lecture for the fun lecture.